I missed, I missed, I made, I missed. And then I just went through and did my percentages. So 0%, 0%, then 50, and then my percentages went 40, 40, 45, 37, 43, 44, 38, 40, and 41. Oh, wait. Where did I mess up? I messed up somewhere. Let's call it 40 and 41. All right, so if I'm using that as my percentages, so if I was graphing this, number of shots on the x-axis, the percentage of the shots that are made, all right? So it starts off at 0, right? By the time I get to 10, it goes up to 40%. 15, it's at 45, so it's going up a little. 20, it's gone down. 30, it's gone down a little more, huh? Nope, up a little bit, sorry. Why did I put it there? I don't know. 30, it's at 43. 40, it's at 44. 50 is at 38. 60 is back at 40. All right, so what do we notice if I connect all this? What can you tell me about what the true percentage of shots I can make is? It's closer to 50, isn't it? So what do you think is more accurate here? These first 10 shots, or when we get closer into 80s and 90s? Why is this more accurate? There's more shots. We see the pattern a little better, right? So predicting a probability with just a few, this is unpredictable. Predictable. Unpredictable when you have a small sample, okay? The larger the sample, the more predictable, because you can see it's starting to level off a little bit over here, isn't it? And I have another applet I could show you that it will go up into the thousands, and you will see it becomes an even line right in the middle, okay? So, how could you make your best guess more accurate? What could we do to make it more accurate? Do it even more, right? Take more samples. More samples. The more samples, the more accurate, for sure. So, based on this, it's looking like it's closer to 40%, right? My set of data. Your data may look different, but mine is 40%. Now it says interpret the probability. So here's the writing, interpreting, all right? So if I interpret a probability, it'll look like this. No, use the highlighter. If Dobbs takes many, yes, we do many free throws, about 40% of them will be makes. If Dobbs takes many free throws, about 40% of them will be good. Okay? What's required when you interpret a probability? Of course, context, right? But wording-wise, many. I know it sounds really stupid, but many whatevers. Free throws, flipping coins, whatever. And then always throw in the word about. You don't ever want to say a probability is exactly this because it's always an estimation, okay? It's probably this. It's about this, approximately this. Any words like that that soften it a little bit, you want that, alrighty? You can see this on the chart here. You can just look at mine. But as we did more, you see it leveled off. It goes towards a value. It's almost like a limit, right? It goes towards a value. It's going to level off at a certain value. But it's a long run frequency. It's not dependent on just a few because it levels off somewhere. That's why we have to have many, many samples, many, many reps, whatever it is. So let's look at this. What is probability? It is the long run relative frequency of an event. All right. So it's a long run relative frequency. It is always between 0 and 1. Because 100% is the highest you can get, 0 is the lowest. You can't have a negative probability, right? Short-term outcomes are unpredictable. We just saw that. Long-term outcomes are more predictable. All right. Long run relative frequency interpretation. Okay, instead of saying long run relative frequency, this is called the law of large numbers. All right, that's what goes here. Law of large numbers. If we do something many, many times, the proportion of desired outcomes will approach its true probability. But you have to do it many, many, meaning a lot of times thousands of times. We don't have time to do it thousands of times, right? Nowadays, there's all kinds of technology that runs simulations for us that will tell us what's going to be if we did it 10,000 times, 20,000 times. And you begin to see it all levels off, all right? So let's look at this application just for a second. This is your introduction. Use the 4 probabilities to complete the middle column of the table. Then give an example of an event that might have this probability. All right, so let's figure out which one of these scenarios has a probability of 0. Outcome is impossible. That can never occur.
0.
Is that a 0? Okay. Give me an example of something that could never occur.
Rolling a 7 on one dice.
There you go. Perfect. Yeah. Rolling a 7 on a die. Yep. Not possible, is it? It's not even on a die. Great. What's the probability that an outcome is certain? It's going to occur every trial. That's a 1. What's an example of something that is for sure going to happen?
Your birthday?
Do you know for sure? Going to have my birthday every year?
Whenever you jump in
You might be dead, but you'll still have them.
That is so dark.
But it's real.
Okay, the sun will come up. I'm just going to be happy.
I was going to say the 11th.
what if it doesn't?
It's coming up somewhere.
Sophia's on to something.
What if it,
She's planning something right there.
but what if, in response to that, there could be a heat explosion that wakes them up?
That's true. Okay. We're gonna go with it now. This is sketchy, right? All right. The outcome is very unlikely, but it will occur once in a while in a long sequence of trials. Which probability would that be? It's unlikely, but it will happen. So 0.3. What'd you say, Jesse?
Jesse passed the test.
Solar eclipse.
That's not true. It's going to be higher than 0.3. Guarantee it.
I mean.
But you offered it. I did not come up with that. You offered it, right? That's not true. That's not true. The outcome will occur more often than not, but it doesn't occur almost every time. Okay. Kenley does what?
Shooting in the 70s.
Kenley, I'm going to put golf, just to be clear what we're shooting, in the 70s. She gets golf score in the 70s. That's great. All right. in the Wheel of Fortune, there is a 1 in 9 or 11.1 probability of spinning bankrupt on any given spin. Interpret the probability. So using the wording I gave you on the front page, how do we start this puppy? If we do what?
If we spin it many times.
Yeah. If we spin the wheel many times, then what? About 11.1% of the time, what's going to happen? Yep, it'll land on bankrupt. Okie doke. In 9 consecutive spins of the Wheel of Fortune, none of the spins land on bankrupt. The next contestant worries that he is more likely to land on bankrupt now because they're due a bankrupt. Why is that wrong? Yeah, the previous spin doesn't change the following spin, does it? No. So we call that independent. Every spin is independent of one another. Doesn't matter what happened previously, they're independent. So when you hear that, oh, we're due a bankrupt, no, you're not. Probability hasn't changed, right? So it's wrong because each spin outcome, I should say, does not depend on the previous spin. We call that independence. You'll hear that a lot in this chapter. Each spin is independent of each other, just like flipping a coin. Each coin flip is independent of the previous, right? Doesn't matter. Easy enough? Intro?